Next, adiabatic process. Work involved. Work involved in adiabatic process. So in order to derive the expression for work involved in the adiabatic process, we have to use certain terms like Cp and Cv. Therefore, let us discuss the meaning of the Cp and Cv and other related terms that we are going to use in this concept. So first, specific heat. Specific heat S. Specific heat S means the ratio between infinitesimally small amount of the heat exchanged between the system and surroundings and temperature. That means here when the system absorbs or liberates infinitesimally small amount of the heat energy at any temperature, the ratio between that small amount of the heat energy exchanged with respect to temperature is called specific heat. But in the normal terminology, we don't define the specific heat in this manner. Simply we will use in a different language, that is quantity of the heat required to rise the temperature by 1 unit is called specific heat. Next, this specific heat we can define with respect to quantity of the substance or with reference to without respect to quantity of the substance. If we define the quantity of the heat with respect to unit quantity of the substance, then it becomes intensive variable. Therefore, if it is defined per unit quantity, then it becomes intensive variable. Therefore, units this dq is so many kilojoules per gram per Kelvin. Next, if the same specific heat is defined per unit mole, if it is defined per unit mole, then it is called molar specific heat. The molar specific heat is represented with the C. It is dou Q by T. Here N, this is per mole. Therefore, units, this is kilojoules per mole per Kelvin. Next, the other aspects of the molar heat capacity. See, molar heat capacity means the quantity of heat required to rise the temperature of 1 mole of a substance by 1 degree Kelvin is called molar heat capacity. Next, the amount of the heat required to rise the temperature by 1 unit depends on the method of conducting the process or depends on the conditions of the system. Therefore, molar heat capacity is path variable. It is a path variable. So, since it is path variable, that means if we change the reaction condition, automatically the amount of the heat required also changes. For example, if we maintain the volume as constant during the course of experimentation, then the molar heat capacity is represented as a Cv. If we maintain pressure as constant, the molar heat capacity is represented as the Cp. Molar heat capacity at a constant volume. So, this is dou Q upon T. Next, at constant volume, already we know that the heat exchanged with the surroundings is equal to internal energy change. Therefore, dou Q is equal to du. Therefore, Cv is equal to du upon T. Next, say for n moles of the gas, n moles of the gas, Cv is equal to n du by T. Cv dt. Next, therefore, change in internal energy is equal to Ncv dt. For finite change, the du is equal to Ncv T2 minus T1. T2 minus T1. If Cv is assumed as constant, Next, molar heat capacity at constant pressure, Cp, dou Q upon T. Next, at constant temperature, the heat changes involved in the process is equal to enthalpy change. Therefore, we have dou Q is equal to enthalpy change. Therefore, Cp is equal to dH by T. Or enthalpy change. Therefore, enthalpy change is equal to Ncp dt. For finite change of temperature, del H is equal to Ncp dt. Work done by the system during adiabatic reversible process. Adiabatic reversible process. In adiabatic reversible process, dou Q is equal to 0. Therefore, according to first law of thermodynamics, dou Q is equal to du minus W. Therefore, this term is 0. Therefore, G is equal to du minus W. Therefore, minus du is equal to minus W, or du is equal to W, that is equal to minus PdV. Now, we want to derive the expression for work. You see, in the adiabatic condition, the dq has become 0, hence internal energy change finally became equal to work involved in the process, or is equal to minus PdV. Therefore, W is equal to du. Next, change in internal energy, already we know that it is equal to Ncv dt. Therefore, W is equal to minus PdV, that is equal to Ncv dt. Next, for finite range of temperature, W is equal to Ncv T2 minus T1. Next, this is the expression for work involved in the adiabatic process. Next, Cv is a variable. Therefore, let us replace this variable with any other term which will remain constant throughout the process. So, for that purpose, now observe this relation. In thermodynamics, we have Cp minus Cv is equal to R. You divide both sides with the Cv. Cp minus Cv by Cv is equal to R upon Cv. This is Cp upon Cv. This is gamma. This is Cv by Cv is equal to 1. This is R upon Cv. Therefore, Cv is equal to R upon gamma minus 1. Therefore, here now you replace this Cv with R upon gamma minus 1. R upon gamma minus 1. T2 minus T1. Therefore, this is the work involved in the adiabatic process. You see, in this term, only the variables are T1 and T2. All the remaining terms are constant. Therefore, by using the expression which is having only constants, we can easily calculate the work involved in the adiabatic process. Next, in this adiabatic process, since the gas is undergoing expansion without absorbing the heat, the final temperature is always less than the initial temperature. Hence, finally, if we calculate the work, you will get the negative result. That means finally the expression will become negative. That means if you get the negative, that implies gas is spending its internal energy. By spending its internal energy, it is doing the work. Here, this is the work inward. Next, if the adiabatic process is reversible, so in certain problems, instead of giving the initial temperature and final temperature, they will give the initial and final pressure and volumes. So by using the pressure and volumes, we have to derive the another expression. Therefore, if adiabatic process is reversible, then relation between pressure, volume and temperature. So for these relations, let us say we have W is equal to du, that is equal to minus P dV. Next, du is equal to minus P dV. du is equal to NCV dt. This is equal to minus P dV. For ideal gas, so for ideal gas, P is equal to nRT by V. Therefore, in place of this, during the reversible process, the pressure of the gas and pressure of the surroundings are same. For that pressure, we are giving the expression. Here P is equal to nRT. Here pressure of gas is equal to pressure of surroundings. Therefore, here NCV dt minus, here in place of P we can substitute that term nRT by V. The next step is NCV dt is equal to minus nRT dV by V. Next, bring this temperature this side. NCV dt by T, and it is equal to minus nR dV by V. Next, for finite change of temperature from T1 to T2. Therefore, NCV dt by T, T1 and T2. This is minus nR dV by V. Here V1 to V2. If the temperature changes from T1 to T2, volume changes from V1 to V2. Therefore, NCV ln T2 by T1. Here we have minus nR ln V2 by V1. Next, NCV ln T2 by T1 is equal to, I'll bring V1 to the numerator. Therefore, expression becomes nR ln V1 by V2. Next, here, so for 1 mole of gas, this N becomes 1, this N becomes 1. Therefore, CV ln T2 by T1 or ln V1 by V2. Next, in the previous case, in place of CV, we substituted R upon gamma minus 1, or else we can represent like this also. Bring R this side, CV upon R ln T2 by T1 ln V1 by V2. The next step, so this ln T2 by T1. So this side and this side, if you eliminate the logarithmic function, it becomes T2 upon T1 raised to the power CV by R. This side V1 by V2. V1 by V2. Next term V1 by V2. Or we can represent like this. You bring V2 this side. V2 T2 upon CV by R. This side V1 T1 CV upon R. CV upon R. Next, in place of CV, we can introduce that R upon gamma minus 1, because earlier we have used this term. We have Cp minus Cv is equal to R. Cv minus Cv is equal to R. On dividing both sides with Cv, Cp by Cv minus Cv by Cv is equal to R upon Cv. This becomes gamma minus 1 R upon Cv. Therefore, Cv is equal to R upon gamma minus 1. R upon gamma minus 1. Therefore, Cv by R. Cv by R. Cv is R upon gamma minus 1. Here denominator R. This R and R will get cancelled. It becomes gamma minus 1. Gamma minus 1. Therefore, V2 T2 gamma minus 1 is equal to V1 T1 gamma minus 1. So, either by using this relation or using this relation T2 Cv by R. We can calculate the temperature changes if you know the volume changes, or we can calculate the volume changes if we can know the temperature changes. But this relation is applicable only for adiabatic reversible expansion. It is not applicable for any adiabatic irreversible process. This is one relation. This is the relation between volume and temperature. The same relation we can represent like this also. This is V into T is equal to constant. Next, a relation between the what is called pressure and volume. So, in order to know the relation between pressure and volume, so we have to replace this temperature term. So, for that purpose, we have PV is equal to nRT. Therefore, T is equal to PV by nR. That means wherever T comes, you can substitute the PV upon nR. Therefore, V2, here in place of T2, you put P2 V2 n upon R raised to the gamma power minus 1. Similarly, here V1, in place of T1, you put the P1 V1 gamma minus 1. So, in a given set of conditions, the quantity of the gas will remain same, R also remains same. Therefore, this expression we can represent like this: V2 power 1 P2 gamma minus 1 V2 gamma minus 1. Next, V1 power 1 P1 gamma minus 1 V1 gamma minus 1. So, W is equal to du, that is equal to minus P dV. We know internal energy change is equal to NCV dt. Here this is in place of pressure, we are substituting the expression for the pressure. So, that is P is equal to nRT by V. Therefore, here minus nRT by V. Next, NCV, bring the temperature this side, NCV dt upon T, NR dV by V, Next, on integration, NCV dt by T between the limits T1 and T2 minus NR dV by V, it is from V1 to V2. Therefore, NCV ln T2 by T1 is equal to minus NR ln V2 by V1. Next, NCV ln T2 by T1 is equal to NR ln V1 by V2. I have inverted the expression. Next, for 1 mole of gas, CV ln T2 by T1 is equal to ln V1 by V2. Next, ln R upon CV ln V1 by V2. Therefore, now this expression we can represent by eliminating this logarithmic function. Therefore, T2 by T1 is equal to V1 upon V2 upon power R upon CV. This R upon CV we can replace with another term like this. We have Cp minus Cv is equal to R. Therefore, Cp minus Cv upon Cv is equal to R upon Cv. Therefore, gamma minus 1 is equal to R upon Cv. Therefore, the above expression can be represented like this: V1 upon V2 raised to the power gamma minus 1. Therefore, T2 V2 raised to the power gamma minus 1 is equal to T1 V1 raised to the power gamma minus 1. This is one expression which shows the relation between temperature and volume. Now, relation between pressure and volume. Now, we have temperature is equal to PV upon NR. Therefore, in place of T2 we can put P2 V2 N upon R. Next, V2 raised to the power gamma minus 1. Here in place of T1 we can put P1 V1 N up R, then V1 raised to the power gamma minus 1. Next, see, for a given gas R is remains constant, quantity of the gas will remain constant. Therefore, this expression we can represent like this: P2 raised to the power 1, V2 raised to the power 1. Next, V2 raised to the power gamma minus 1. Here P1 raised to the power 1, V1 raised to the power 1. Next, V1 raised to the power gamma minus 1. Therefore, this V2 raised to the power 1, V2 raised to the gamma minus 1 becomes V2 raised to the power gamma. This will remain P2 raised to the power 1. Here P1 raised to the power 1, V1 raised to the power gamma. Or this expression we can represent it as PV power gamma is equal to constant. This expression we can use it to study the relation between pressure and volume, or in any numerical problem if the initial and final volumes are given, if they ask the pressure ratio or if they ask the final pressure, we can use this relation. Next, relation between the pressure and temperature. Pressure and temperature. So, this is the expression: PV power gamma is equal to constant P2 V2 raised to the power is equal to P1 V1 raised to the power. Now we want to introduce the temperature term. Now we are studying the relation between pressure and temperature. Therefore, introduce the temperature term in place of the volume. Now here we have from ideal gas equation PV is equal to nRT. Therefore, V is equal to nRT by P. Therefore, in place of the volume we can substitute this term. Therefore, here P2, here in place of V2 you put nR T2 by P2 raised to the power gamma is equal to P1, here nR, here T1, P1. Next step, see the number of moles of the gas will remain same, R will remain same. Therefore, next step, P2 raised to the power 1, here T2 raised to the power gamma. Here bring P2 to the numerator. So when P2 is brought to the numerator, it becomes minus gamma. Here P1, next T1, you bring P1 to the numerator. This is P1 minus gamma. Next, this is P2 1 minus gamma, T2 power gamma. This side P1 1 minus gamma, T1 gamma, or P power gamma 1 minus gamma, T power gamma is equal to constant. So therefore we can use this relation, or we can use this relation to study the relation between pressure and temperature in the adiabatic reversible process. Therefore, the three relations what we have derived so far, they are applicable only for adiabatic reversible process only. Don't use it for adiabatic irreversible process.